Hey folks, okay, I'm back at it. All right, I've got my hat on. I'm ready to go. You don't want to see my ugly looking head unless you're into that sort of thing, like you're into all the nasty stuff. I've got an awesome Halloween costume in the works. In any event, let's get right into it. Okay, so continuing along in our discussion of phase changes, and I want to get into more of the descriptive component of phase changes. Okay, so no math on this lecture. We're just going to talk about some of these phases and what they mean. Actually, I lied. There's just a little tiny bit of math, and that's the Gibbs phase rule. Okay, so let's get into that right away. So Gibbs phase rule has an equation. It's the following: F equals C minus P plus 2. Okay, so what do all those letters mean? Okay, well, C is the number of components. Okay, so in other words, is it a pure phase? So if it's a pure, I shouldn't say pure phase, if it's a pure material, then that means C equals 1. There's just one thing, like water or helium or carbon dioxide. But we certainly can have multi-component phase diagrams. So that's very common, especially with lipids and proteins. You'll see that when you add things like water and salt to those types of materials, it can really change their structure. So for everything we're doing in this class, we're just going to stick with one component phase diagrams. In the next couple chapters, we'll see what happens when we have multi-component phase diagrams. Okay, so P is the number of phases for the letter P. Okay, and that's pretty descriptive, right? If it's a liquid, that's one phase. But for example, if you're at, let's say, the triple point, there's 3 phases at the triple point. Or for example, if you're on one of these phase boundaries, let's say you're somewhere like right there, that's technically 2 phases. You're in a situation where the vapor and the liquid are in equilibrium with each other. Okay. And so last, F is the number of degrees of freedom. And this isn't quite the same degrees of freedom like what we talked about with rotations and vibrations and so forth. This degrees of freedom is really like how many things can I change and still maintain the same phase. Okay, so for example, if I'm somewhere like right in here, let's say I'm at this point, then I have 2 degrees of freedom. I have changes in temperature. So I could change the temperature, so that counts as 1 degree of freedom. Or I could change the pressure. Okay, so that counts as a degree of freedom. But if I'm at, one of these points right here, then that changes my degrees of freedom. For example, at the triple point, you have 0 degrees of freedom. You can't change the temperature or pressure at the triple point and still maintain the triple point. Okay, so let's work through a fictitious example. Okay, so this is an activity. So I identify the number of phases and degrees of freedom at each point indicated on the graph. Okay, so we've got A, B, C, and D. So here's point A right here on this line. Here's point B at the intersection of phase A alpha, phase beta, and phase delta. Here is point C, which is actually now the intersection of phase delta, beta, gamma, and phase eta. And point D, right, is like right there in the middle of phase alpha. Okay. So first, let's identify the number of phases for each of these. So P, because the equation, right, recall, is F equals C minus P plus 2. So we know for everything here, C equals 1. So this is a one-component phase diagram. Okay. So what about at point A? Well, at point A, it's on one of these phase boundaries. So there are two phases in equilibrium with each other. Okay. Phase alpha and phase beta are in equilibrium with each other at that point A. What about point B? Well, it would be 3. Right? You can see there's phase delta, phase alpha, and phase beta. Okay, what about point C? Well, that's 4 phases right there, right? So that's right phase delta, beta, eta, and gamma. And then at point D, there's just 1 phase indicated by that set of conditions. So now what about the degrees of freedom? Okay, well here A, so we'll say F equals 1 minus 2 plus 2, so that equals 1. Okay, and we're going to talk about what all that means in a second. Okay, so for point B, F equals, okay, the number of components is C, right? And that's, let's see, minus 3 plus 2, and that equals 0. Okay, for, we'll say A. For B. Okay, what about for C? Well, F equals 1 minus 4 plus 2, and that actually gives me -1, and we'll talk about what that means in a moment. Okay, and then finally, point D, I get F equals 1 minus 1 plus 2, and that equals 2. Okay, so what does all of this mean? Well, at point A, I only have 1 degree of freedom right there. And what that 1 degree of freedom means, I can't change the pressure without correspondingly having a change in temperature if I want to maintain having those 2 phases in equilibrium with each other, right? So in other words, if I'm changing the temperature and I want to stay on this point, I have to change the pressure as well, okay? So in other words, I have to change P of T, right? So I have to, if I'm changing T, then P is going to respond to that as a consequence, if I want to stay on that line. What about point B? Well, point B, 0 degrees of freedom, that's a triple point, okay? So I'm going to say TRP, triple point. I can't change the pressure or temperature at that point and still make it a triple point. So there's 0 degrees of freedom. I can't change temperature or pressure and still maintain that point. What about this point C? Well, you might be thinking, is that a quadruple point? And no, this thing is fictitious, cannot exist. DNE does not exist. Okay, so I told you this was a fictitious phase diagram. And yes, as we will see, as we learn from Gibbs phase equilibria, Gibbs phase rule, you cannot have 4 phases in equilibrium. Can't do it. Okay, we can have 3 phases in equilibrium, but we cannot have 4 phases in equilibrium. It does not work. Okay, and now what about point D? Well, point D has 2 degrees of freedom, and that means at this point D, I could maintain the temperature and change the pressure up or down, provided that I don't hit some boundary. Or I could maintain the pressure and change the temperature up or down as long as I don't hit one of those boundaries, okay? So that's what all of this means with the Gibbs phase equilibria. And as it turns out, this holds even in really complicated phase diagrams, okay? So I'm going to move past that, and I'm going to do more descriptions, qualitative descriptions of 3 examples: water, carbon dioxide, and helium. And I've got some really cool videos to share with you all. So first of all, here is the H2o phase diagram. Notice it is a humongous pressure scale. This is a log scale, going from 1 Pascal to 1 terapascal. That's 1 times 10 to the 12th pascals. That's a lot of pressure. That's 10 megabar of pressure, okay? And check it out, on this phase diagram, look, here is 1 bar, there is roughly atmospheric pressure, okay? And this is what you're going to do in Igor 3. We're going to construct a phase diagram, just like this, okay? We notice here that if I scan across the atmospheric pressure, we get to the normal boiling point, right? 373.15 Kelvin, 100 degrees C, okay? And if I keep scanning across that atmospheric pressure line, roughly, right, there is also now my normal freezing point, okay? So consider, right, 1 bar is a 101.325 kilopascal, right? Which is not quite atmospheric pressure, but very close. It definitely is standard pressure, okay? So now let's see here. So 273.15 Kelvin, right, there's our normal freezing point, okay? And for water, what's pretty cool, we can see the triple point, 273.16 and 611.657 Pascal. So that's vacuum, right? So if 100 kilopascal is atmosphere, this is way down on the vacuum scale, okay? So roughly 10 millibars, so that's like roughly 0.001 ATM for the triple point of water, okay? And now if we scan up, we can see, oh look, there's the critical point. And yes, that's PC, TC, and of course we don't see on this scale VC, those things that we were calculating using van der Waal and so forth, okay? And what ends up happening at the critical point, and this phase diagram doesn't go much past the critical point, but I've got a really cool video to show you what happens at the critical point. The liquid and the vapor have the same density, okay? And there ends up being a really cool consequence as a result, okay? So the density of the liquid and the vapor is the same at the critical point, which is really cool. And now what you notice going on here for water, there is a whole complicated mess of different solid structures. We're normally used to seeing this IH, that's I-hexagonal. It's got a hexagonal lattice, okay? But it can also have a cubic lattice, that's what that IC means. It can have an orthorhombic lattice. And if you remember all of those things from George's class, then maybe that's somewhat familiar, okay? So I'm not going to go into all of these details, all these different crystal structures, but we will talk about those types of phase diagrams soon. So in other words, our normal phase equilibria, right, our solid to vapor, or our liquid to vapor, or our solid to vapor, that's what I'm going to start calling first order phase changes, okay? First order. And I'll just say that's like the normal stuff that we're used to, boiling, freezing, and so forth. All of these solid to solid phase transitions, so for example, like the phase transition from this IC solid phase to this XI solid phase, that's called a second order phase transition. And we'll see more examples of that in the coming lectures, okay? So I'm going to switch over to carbon dioxide, but little did you know how complicated water actually is, okay? So moving on. So now here's CO2. It's not quite as detailed of a diagram, but what you can see here, biggest noticeable difference, look, the boundary between the solid and the liquid has a positive slope. And I didn't talk about this here. It's really hard to see it on this scale. But as it turns out in water, the liquid and the solid boundary actually has a negative slope. That is the indication that the solid phase of water is less dense than the liquid phase, which is rare, right? Everything else has a positive slope right here between the solid and liquid phase, because everything else has a solid phase that is more dense than the liquid phase. There are other examples like water, but they're extremely rare. There are things like the I'm going to get some of these wrong. I'll have to look these up and get back to you on that. But there are so few and rare examples like water. Everything else, nearly everything else, has a positive slope, indicating the solid phase is more dense than the liquid phase. Okay? So I'll point out here, you can see the triple point of CO2 at 5 atmospheres and negative 56 degrees Celsius. What's cool, what's interesting, what I want to use to discuss this supercritical fluid point, right? Check it out. So again, this is TC and PC. It's pretty convenient where this occurs. And convenient meaning these are conditions that are easy to reproduce in a laboratory. 31 degrees Celsius and 73 atmospheres, that's fairly convenient to reproduce. So quick math, 73 atmospheres is about 1,000 pounds per square inch. When you buy a cylinder of carbon dioxide, they're often filled with 2,000 pounds per square inch. Okay, so getting the critical point and thus creating supercritical CO2 is pretty convenient. And there are a lot of amazing things you can do with supercritical CO2. So I have a video that I'm going to share with you all. I'm not going to play the full video, but I did add this to our playlist and on my YouTube channel. And what I'm going to point out here, so I'll just kind of describe what this guy's got going on. He's got a chamber and it's filled with liquid CO2 as well as gaseous CO2. So you can see here that liquid line right there. That's the liquid, and above that liquid is vapor, is CO2 gas, right? And you can see right there he's got a thermocouple in there. So right now this chamber is 24 degrees Celsius. It's really hard to see what the pressure is on that scale, but it's sufficiently large that he's going to be able to make the supercritical CO2. Okay, and so watch what happens as he heats this up. This is really cool.
CO2 is starting to boil in there.
Temperature's going up. Watch what happens at 31 or 32 or so, you guys. It's really cool.
Okay, now the boiling has pretty much stopped. You can still see some density changes in the liquid there, but at this point there's no more bubbles, and the transition from the liquid to the gas phase in there is almost gone.
Oh, and look at the pressure's going up. I saw the scale go up. Look at that. The boundary is gone.
And as you can see, something interesting has happened. There's no more dividing line between liquid and gas inside there.
Cool stuff.
So I'm going to unplug the heater.
So I can't remember how long it takes him to drop it down back below, but we'll watch for a few minutes.
Cloudiness to subside.
So you can see it's cooling down.
What we're left with here is one phase basically inside the chamber. The CO2 has gone supercritical, meaning that the density between the liquid phase and the gas phase eventually became so similar that they blended together. So it's all one continuous phase in there now. Now to transition back, what I'm going to use is just a piece of dry ice, and I'm going to hold it against the
more CO2
aluminum on the outside here to bring the temperature down quickly. So check this out. Surprisingly, this actually works better with just water ice, since it melts and makes a nice contact between the aluminum and the ice cube.
There you go. Back to liquid CO2.
Back to two phases.
Okay, so that is really, really awesome. It's not cool because it's actually 31 degrees Celsius, right? So what can you do with supercritical CO2? So some of you already know the answer to this, and you probably are thinking, I can extract marijuana, and that's right, you can. Or you can extract THC from marijuana using supercritical CO2. There's also a lot of other things that you can extract out of material with supercritical CO2. And the reason for that is it becomes an ideal solvent for organic molecules when it's a supercritical fluid. So in other words, it has the same density, right? The liquid and the gas have the same density, and this makes it extremely viscous, okay? So if you have some other organic material, like a plant or a flower, right? This supercritical fluid can actually penetrate, through like the cellulose and through those structures of the plant and actually dissolve the material that's inside there, particularly, let's say, the THC in the case of cannabis. You can also extract flavonoids and flavor molecules from other types of materials. So people do a lot of supercritical CO2 extraction on hops and barley to get certain molecules out that they want. And of course, you can't tell it, I only want this molecule to be extracted out. You get everything out of there, right? When you put some organic material into a supercritical CO2 chamber, it's going to pull out everything. So you then from there have to use your organic chemistry skills to separate all of those compounds that you pulled out by the boiling points. So I actually did some of this in grad school. I didn't do this on cannabis, but I did this on natural materials. We use supercritical CO2 to extract fatty acids out of soybeans. And we did this actually for a class. I didn't do it for my research. It was for PChem lab, which I was the grad student TA of. But it was a mess. It turns soybeans into just an organic, soupy mess. But it is very cool. You can run that stuff on a mass spec or a GCMS, separate out all the materials based on their boiling points. So supercritical CO2 is a really cool industrial material for solvents. It's a wonderful solvent for organic material. Okay, so the next one I want to talk about, helium. This one is very cool, as it turns out. So you notice, right, like 2, 3, 4, 5, 6 Kelvin, cool. Okay, so here the triple point at helium occurs a shade above 2 Kelvin and at a pretty easy vacuum to achieve in the lab. But now you notice there's this interesting thing called a lambda line. I'll get more into what that lambda line means in the next coming lectures. But what you have at that lambda line, and check this out, right at 1 bar, that's roughly atmospheric pressure. It's right there, okay? And on the other side of that, it's a superfluid. So just warmer than 2 Kelvin, it's just regular old liquid helium. So what is a superfluid? So I have another pretty cool short YouTube video that I'm going to share with you that talks about what a superfluid is and shows you liquid helium as a superfluid. This is awesome, you guys.
And as the pressure drops above the
so this
helium,
is boiling liquid helium right
so
here.
Eventually this will drop down to about 2.17 degrees above absolute zero. And something magical happens there when it turns from this normal kind of helium into a helium called superfluid.
What happens then? It goes sort of still.
Yes, completely still. Yeah.
Oh wow!
There
It's
it
going
is,
completely
completely
still.
still.
It's gone
It's gone
completely
through this
still.
position now.
Yeah.
That is now sitting there at 2.17 degrees above absolute zero.
So that whole clear liquid is liquid helium
Still.
at
Because
2
the entire
Kelvin.
liquid is sitting there at the same temperature.
And what is it? You know, what am I looking at? It doesn't look like a liquid almost.
No, well, what's happening here is that every single atom in that helium liquid is sitting there behaving in what's called a cooperative state. They're all behaving together.
Yeah.
So that nowhere is a different temperature. Everything's the same temperature.
So I want to clarify what he's saying there. He's saying nowhere is a different temperature. Okay? What he's really getting at is this, this canonical ensemble idea that literally every atom is the same. That is in contrast to what Boltzmann says. Boltzmann says there's a distribution of these energies or these temperatures, right? There should be some average value, okay? But this material, it's become so cold, there's no longer a population of states. You could think of this as it's got one microstate as a superfluid, okay? And there are some amazing consequences as a result. Check it out. And so also to describe, he's got that little glass capsule that you see there, that also contains a solid piece of glass on the bottom, okay? But a superfluid has no viscosity, none. So what that means is there's no friction between the individual atoms, and there's no friction between the atoms and the container. So there's no more adhesive or cohesive forces. And any teeny tiny nanometer-sized defects in the glass are now places where that superfluid can just pass right through. I'm serious. It can just pass right through the glass as if it weren't even there. Pretty amazing stuff. Pretty amazing stuff. So there's tons of videos out there on supercritical CO2 as well as helium as a superfluid. If this inspired you, you'll find a ton of awesome videos on those two things, and I would encourage you to explore that. So I think that's all that I wanted to do with this lecture. I wanted to keep it nice and qualitative. So the next one, there will be math. Okay, folks. I'll see you later.